in this example, which is given here in this diagram, the car starts its speed, it goes up, like some speed is up there, and then it is eventually moving it down and so up and again like that. So whenever you are looking for the average is going to be somewhere at the middle of the lowest points and the peaks, right? The highest points and the lowest points. This is the dotted line is showing us the average. But what is instantaneous? Instantaneous is the speed right there at that moment of time. Whatever your car odometer reads, that's the time. That's the speed what you want to see, okay? So the instantaneous velocity of a particle at a particular instant is the velocity of the particle at that instant, okay? So what is actually means that if you are going with the 100 kilometer per hour, your odometer reads 100 kilometer per hour. So that's your speed. This is your speed at that moment of time, okay? So that's why we are calling it instantaneous. So here, when I'm writing this velocity, remember that I can write this as a delta x, okay, divided by delta t. So whenever we are talking the instant, all it means that this time interval is so small, like you are not looking for 1 hour time interval. It will be more like a fraction of a second. So when it becomes to a fraction of a second or almost approaching to zero, then you are saying that the t is almost approaching to zero. So in mathematics, in your math 101, what you may have learned that when you are having delta, it means that you are talking about large interval of time or large interval of things. But if this limit is applied, the limit delta approach to zero, then you have another symbols used for that. It will be dx by dt. And again, the vector notations all will go with it. So here, this will be our notation, which is literally the derivative that you are using in physics, the math 101. Okay, so we will be using derivative for this purpose. Instantaneous velocity is the slope of the tangent of the position time graph at that particular instant of time. So this statement may not be understandable at this point, but I can explain it in the next slide. The instantaneous speed is the magnitude of instantaneous velocity and has been stripped off of any indication of the direction, either in words or in algebraic sign. Recall that we talked about two things. One was the average velocity and average speed. In that situation, the average velocity and average speed both changes drastically from each other, because the distance covered, it is completely different than the displacement, right? But whenever we are talking about the instantaneous speed and instantaneous velocity, these two are the same things, okay? But here in the velocity section, you are having the direction, while in the speed section, you will not have any direction. So when we are talking about the physical quantity of the speed, it is v, means that we are taking the magnitude of the velocity. And here on the right side, I'm writing exactly the same way as I'm writing the equation for the velocity, except there is no arrow on it. Do you guys have any question on this slide?
Yes, Doctor.
Yeah.
Do we have to know from where we got dx over dt?
Yeah. So this is the mathematical limits. Like whenever you are applying the limits means, let me put in this way. If you are going from your home to a shopping market and it takes you, let's say, 30 minutes. So the delta t here, it accounts for all those 30 minutes, okay?
Okay.
But whenever you are talking about the instantaneous, it means that you are just talking about that instant of time. Like when you look at the clock, what is my time? So this is the instant. That is the instant at which you looked at the clock, right? So your odometer, if you look at that, when you are moving your car, whatever you see, that's your instantaneous speed. So in that, the time record is a fraction of a second, or almost approaching to zero. So this will be much smaller time interval as compared to delta t. Did you get this point?
Yes.
Okay. Here, this checkpoint, the following equation give the position x of a particle in 4 situations. These are the things, 4 different equations we have. Equation 1, 2, and 3, 4. In which situation is the velocity of the particle constant? And in which is v in the negative x direction? So I'm going to do 1 for you, and then we'll be asking the questions for 2, 3, and 4 from you guys. Here the displacement is shown. It is for the position 1, it is x equal to 3t minus 2. And we know that the instantaneous velocity is this the dx by dt. You are taking the derivative of t. So again, you are putting here this 3t minus 2. This equation you put inside, okay? So you know by mathematics, when you apply the derivative, the constant will come out and you apply the derivative to the variable. And again, if you apply the derivative to the constant here, let's say, then what you are getting is 0. So dt by dt, it's giving us 1. So I'll be left with the answer 3. Is this 3 a positive quantity or a negative quantity?
Positive.
Positive quantity. So in the first situation, when they are saying that in which situation is the velocity of the particle constant, so we can definitely say that in situation 1, it is constant. Okay. How about situation 2?
It's not constant.
It is not constant because you will get the derivative of t squared, which will be 2t. So 8t, right? So it will be again
minus 80.
Yeah. And how about the third situation?
It's not
non-constant.
Okay, not constant. What? Well, how about 4?
4 will be constant.
4. It's
In 4, what is the answer?
0.
Will be 0.
Maybe
0. Is the 0
0.
constant?
No.
Yes.
Yes.
Yeah,
will
it
be
is,
0,
right?
yeah.
0 is
Yeah.
constant. So therefore, in the fourth situation, it is also constant. Now, when it comes to the negative, so then I solve these problems. Here you see that the negative sign appears here, which is explicitly showing you these two, situation 2 and 3, the velocities are negative. No matter what time you put here, because the time is as a positive quantity. So all the time, the answer you will get, it will be negative. All right. This is an example here. In figure 2.6a is an X plot for an elevator cab that is initially stationary. Then it moves upward, which takes to be a positive direction for X, and then stops. Plot V. So if you look at this graph, the graph here on the y-axis, it is the position, and on the x-axis, we have time. So it is the position versus time graph. And the elevator, what it shows that initially it was at ground level, which is 0. We are considering is 0. And then from here, when it starts to move, you see that in the each passing interval of time, the elevator covers a little more distance. So it comes into some speed. Once it picks up this speed, from here to this much, it is almost a straight line. Like it's definitely a straight line from here to here. At this point, when it comes to the destination, the elevator is stopping. And then with each passing interval of time, the elevator covers less distance, which is kind of inclined like this, okay? So whenever we are plotting this kind of situation, we definitely know that the elevator is at rest here and here. So it means that the velocity is 0 and velocity is 0 at these two ends. So whenever I'm plotting this, it's going to be velocity versus time graph. So at the 1 second, which is here, 1 second, the velocity is 0. And we also see that at 9 seconds, it is definitely 0 again. So at 9 seconds, it is 0. From here onward, the elevator is stopped. In between, I don't know how to calculate this at this point, okay, because we didn't show you how to deal with the acceleration. But from here to here, I can calculate velocity. So let's choose these points on the graph. One is the point B and another one is the point C, and determine the velocity for this. Okay. So if I'm choosing those 2 points, the points are already shown. Here is the x is 24, and I am subtracting the 4 from the x, and the time interval for the position C, it is 8 seconds, and I'm subtracting the 3 seconds from that. So here you see that it is 20 divided by 5. It gives me 4 meters per second. So what I got is that in this straight line location from B to C, the elevator had 4 meters per second speed. Okay. So therefore, when I'm plotting the velocity meter per second on the y-axis, and here was the 4, then I can definitely see that from 3, which is here, let's say it is 3, and the last point is 8, which is here, 8 seconds. I will sketch this line upward, okay? We'll reach it to the 4, and from here 4 to 4, I can plot a straight line. So this is a constant velocity. Now in between, from here to here, we know that it is acceleration. So we just connect these 2 points without further details. We don't put any details to this question any further. So this is the kind of graph that we have, okay? And then in the next slides, when we go to the acceleration section, we will be interested to know how to calculate this section, okay? That techniques I will be showing you. Let's solve this problem first and then proceed further. A car moves uphill with the 40 kilometers per hour and then back downhills with 60 kilometers per hour. What is the average speed for the round trip? So this is one of the problems which appeared in an exam. So I'm showing you this velocity, so this speed is 40 kilometers per hour, and the V2 is 60 kilometers per hour.
Oh, sir, isn't it going to be negative 40? Because it's uphill.
What is that?
Isn't the velocity going to be negative 40?
Yeah, if this was velocity, it will be negative and positive. But if you look at the question, they are talking about the speed.
Oh, okay. Okay.
Yeah. So we know that the average speed, whenever we are calculating it, we are taking the total distance, which is uphill, distance uphill, distance downhill, okay? And then divided by the time taken uphill plus the time taken downhill. Okay, this is the equation what we have here. Now, how many things I know I had and how many things I need to find out? First of all, I know that since the car has covered this equal amount of distance while going upward and downward, this is the only thing which I know. And also I know the 2 speeds. So I will look at the times here, and we know that the V is equal to D divided by T. So if I'm solving this for the T, it will be D divided by V, okay? So here in this question, I will be putting it like this. D plus D divided by D plus V up and D plus V down, okay? V down, V down, okay? You know that the uphill and downhill, the distance is the same, so therefore I could put this D everywhere. I'm taking the D common. The D is taken common. I will left with 1 plus 1 is 2. divided by, again, I'm taking d common, and I will left with the v up plus 1 over v down. Okay, so d cancels out. If you look at this equation, here we have 2, which is the denominator, it is constant. And also in the denominator, v up and v down, these are two constants. These are two given quantities. There is nothing unknown. Can you do this problem now? Will you be able to handle this problem?
Yes. Yes.
Yes.
Okay. This is the solution. Look at this one.
Doctor,
Yes.
from where did we get the D2?
Yeah. You see that this equation here, it is d up and d down. And the car,
yes.
while going it up and coming down, it covers the same amount of distance. So the d up is equal to d down. That's what I put, right?
Yeah,
So
okay.
here you will have d plus d, which will be 2d.
Yes. Thank you.
Yeah. And then when you put for the v up and v down, the values which are given in the problem, just solve it for that. And then we are getting 48 kilometers per hour. Is my speed a little bit faster for you guys, or it is okay?
It's okay.
Okay.
It's okay.
Okay. Let me know if you don't understand any step, you can ask. You can stop me anytime and ask your questions.
Doctor,
Yeah.
this type of answer can only if the distance up and distance down is equal.
What is that?
This solution I can apply it if only the distance up and the distance down are equal.
Yeah, you can apply this for the equal distance. If this was meant for different distances, then they should give you enough data to solve it. If these are two different distances, you don't have enough data. There are two unknowns in the problem, and you need two independent equations for that purpose.
Okay.
Yeah. Okay. So average and instantaneous accelerations. The concept of this is the same as we have just developed the concept for the average and instantaneous velocities. Okay. But here, you know that when you are moving, let's say you are moving with the 20 kilometer per hour, that's your speed. All of a sudden, you decided to move with the 100 kilometer per hour, right? What you do is that you push the gasoline pedal in your car and then you accelerate your car to 100 kilometer. So while going from the 20 kilometer per hour to 100 kilometer per hour, you definitely change your speed during some time. So some of the cars, they can cover that much speed in, let's say, in 1 minute. So here, when we are talking about that kind of time interval in that kind of two speeds, the process what you actually applied there, that you accelerated your car. So what we are saying is that you have V2, which was the 100 kilometer per hour, minus V1, which was initially 20 kilometer per hour, and then you put this in the 1 minute time interval, right? So 100 minus 20 divided by 1 minute. You can easily go with this to be 80 kilometer per minute. If you want to keep this in minutes, yes, it's fine. Otherwise, you can convert it to seconds. This 100 kilometer per hour, sorry, this was a per hour. So I need to do something else here a little bit. But for the shot, it was 1 minute, okay? So here you have per hour, and here you have 1 minute. You need to convert this to hour. And then we know that in 1 hour, there are 60 seconds, 60 minutes. So the minutes cancels out, right? Here what we will do is that we have 80 times 60 kilometer per hour times hour. Look at the time unit now. It's not only hour, it's hour times hour. So here you have 4,800 kilometer per hour square. And you can easily translate it to meter per second square if you want to. If you want this unit to be expressed in the meter per second square, yes, you can do this. And the conversion method is the same as I did there. So here, whenever you see this unit meter per second square, this is the unit of the acceleration. But what you do is that now you are taking the difference of the velocity divided by the time interval. And when you do this, you potentially divided this the displacement 2 times by the time intervals. So that's why you have the 2 times the seconds. Okay? So this is called acceleration. Average acceleration is the change in the velocity over the change over time. And hence, in this example, we have V1 is our first velocity and V2 is another velocity, 8 times 2. And if you want to go with the instantaneous, the process is the same as we used to apply in the velocity sections. But here, again, the time interval, which is delta t, now will approach to 0. And for that this small time interval, we can easily translate this acceleration to be delta v by delta t to be delta v by delta t, right? This is what we have. But you guys also remember that in the last slide, what we were talking about the velocity is the displacement divided by time. And that was, in fact, the derivative of the displacement with respect to time. So when we put that equation from the previous slides, which is here, right here, from this slide into that, like here, what we will get is the 2 times the derivative of the displacement. So instead of now taking the derivative of the displacement 1 time, you need to take 1 more time. And then that will be giving you the instantaneous velocity in this situation. Okay? What is the SI unit for the acceleration? As I stated here, it will be always distance divided by time square, no matter what unit you use, either kilometer per hour square or some meter per second squares or any other unit you can use. It will be at the end, the dimensions of this should match with the distance divided by time square. Okay, now there are 2 things. When you are driving your car, you do 2 things. Either you accelerate your car, or other time you are bringing the car to a stop. So in the general common language, what we use normally, we say that accelerate the car or decelerate the car. Okay? So we normally say that whenever there is acceleration, we say it's a positive acceleration when the car is going becoming faster after every passing interval of time. And when we say the negative acceleration, we literally mean that the car is coming to a stop. So that is negative acceleration. But there is a little bit conflict when we come into the physics and discussing the concepts. If a particle has the same sign for velocity and acceleration, in that case, the particle is speeding up. Okay, just note this thing. When you have the same sign for the velocity and acceleration, then the car will be speeding up. Whenever you have the opposite sign for the velocity and acceleration, then the car will be speeding down. And then you might be confused, like how it is so. So let me explain this with an example here. The sign of an acceleration indicates a direction. Okay, that's one thing which we knew for sure. Not whether an object is speeding up in the increasing speed is increasing or decreasing. For example, if you have a car and that goes in the negative x direction with 25 meters per second, it brakes and the speed is coming down to 0 when it comes to a stop. And the time interval in which it comes to a stop, that is only 5 seconds. So here in applying this equation which we use, we want to determine the acceleration, right? So the acceleration is going to be v2 minus v1 divided by t2 minus t1. So v2 is 0, okay, because it comes to a stop. And then the initial speed is minus 25. And we already know that the time interval is 5 seconds. So here we apply that. Negative times negative, it will become positive. So it will be 25 divided by 5, and the answer is 5. And here you see that it is 5 meter per second square. The sign of the acceleration is positive. This is what we want to emphasize here. The sign of the acceleration is positive, but the car has come to a stop. So the sign of acceleration alone is not enough to tell whether the car is speeding up or slowing down. We need to look at the sign of the acceleration and velocity both together and decide based on that whether the car is speeding up or slowing down. Okay. Any question here?
Yes, I have a question.
Yeah.
Which velocity I need to look at its sign, the second velocity or the first?
You need to look at the two velocities here. It's the first as well as the second. If the sign of the first and the second velocities were the same, then it would mean that the car is still going in the same direction. If the velocity of the first and the second velocities were different, the signs of the first and second velocities were different, then that would mean that your car was swinging, means that it came somehow to the positive direction, it stopped somewhere, and then now it's going backward. So in that situation, you are looking at two different instances, okay? So in that, you will be able to split the situation initially when the car is going and coming to a stop, and then from the stop backward. Did you understand the point?
Yes, thank you.
Okay. Any other question, guys? Okay. Let's proceed here. Why acceleration we are so much playing? And I think you engineers are more familiar with it. Okay. Whenever you are designing a roller coaster, then you may have noticed quite obviously that the roller coaster doesn't go in a straight way. Most of the time, the roller coaster is the curls, right? And more the turns are the better for the amusement. Why it is so? And this is just because that our bodies do not react to velocities that much as compared to acceleration. For example, you are going with the 100 kilometer per hour, or sometimes you can go with the 200 kilometer per hour. Let's say you reach to that. In both situations, your body is not reacting that much. You are still intact with your car seat. For example, you are going in the plane. The plane is obviously going with the 500 kilometer per hour or even faster. But your body is not reacting to that so much. You can comfortably walk inside the airplane from one seat to another seat, right? But if your friend is going with even with 100 kilometers per hour and he's swinging the car, then you will be jaggled, right? And a lot of time your body can react to that, and then you can either feel good or bad about that, right? So those are the situation in which whenever there is abrupt direction change, there is an acceleration involved, and we will come into this point later. But the point for all the conclusion is that if you go to any amusement park, either these are the swings or the rotations or the merry-go-rounds or this kind of roller coaster, all of them will be curled such that you experience more acceleration rather than the velocities. Okay, a particle position at the x-axis is given in by this equation, which is 4 minus 27t plus t cubed, with x in meters and t in seconds. Because position x depends on time, the particle must be moving. Find the particle velocity function of time, and also the acceleration is a function of time. Okay, here this is given to us, okay, this equation. And I will be going and solving this problem with your input. I'm not solving it alone, so you need to provide me what needs to be done here, okay? I'm just writing the first equation. X is equal to 4 minus 27t plus t cubed. The first thing I want to do is to determine velocity is a function of time. So what should I do here with this equation?
I need to take the derivative. Yeah.
Okay, so take the derivative, which is the dx by dt. Excellent. So that's a very good question here. Whenever we take the derivative of the first term, it will become 0 minus 27 dt by dt. I'm going in detail for the first time, and then the second one I may go a little bit faster. Okay, so you know that.
Teacher, the power doesn't it go down?
Yeah, it will, but I didn't apply the derivative yet.
Oh, okay.
Yeah. So here dt by dt, it is 1 plus, whenever we take a derivative of this, it will be 3t squared, right? So minus 27 plus 3t squared. This is what we get for the velocity as a function of time. Now I want to take the acceleration. What should be done?
The second derivative.
Second derivative. So now we take the second derivative of the velocity with respect to t now. So you know that the first term is now constant. Obviously, it will be 0. And the second term, we have 3. And when we apply the derivative, you know that it will be 2t. So 3 times 2 is a 6t. Okay. Did you understand this step?
Yes.
Okay. Yes. So 6t is the acceleration for us, and it is also time dependent. So therefore, it is time dependent acceleration here.
Teacher,
Yeah.
I don't understand this question.
The second part or the first part?
Both.
Okay. Do you see the slides here? This
Yes.
one? Okay. So you take this equation, right? X equal to 4 minus 27t plus t cubed. This is the equation you started with. And we know that whenever we are talking about velocity, velocity is the time derivative of the position vector. Okay? So when you take the time derivative of this equation, like you did take derivative of this equation with respect to time, what do you get from the first term? This first term?
0.
0. And what do you get from this term? You see it's minus 27t, right?
Yes.
So what will you get here?
Minus 27.
Yes, exactly. So this is minus 27 there. Here you have. And when you take the derivative of the third term, then the power 3 will come down, like as I shown here. And then when you take the derivative, it decreases the power by 1, right? 3 minus 1, so which is 2. 3t squared. Did you understand the step now?
Yes.
Mr.
Yes.
Why the 4 has changed to 0? I didn't understand this one.
Why? Okay. You know that there is a difference between constant and variable, right?
Yes.
Constant are those terms which does not change with respect to time. Like let's say you have a chair in your room, and that chair is a constant thing, like it is always there. It doesn't change its shape. Okay? So either you look at now or you look at 1 hour after, it is still the chair. It doesn't change. But on the other hand, if you put ice inside your room, the ice is going to melt. So with respect to time, there is a change in the shape of the ice with respect to time. Okay? So if I take the derivative of the chair will give me 0 because there is no change in the shape of the chair. Okay?
Okay.
Whenever I take the derivative of the ice with respect to t, and then it will give me non-zero value. There will be some value of this because the shape of the ice definitely has changed in time. Did you understand the step now?
Yeah, thank you.
Okay. So now this is the first step. We have the velocity and we have the acceleration. And now I go to the second step. This says, is there ever a time when the v is equal to 0? So whenever, though the answer is obviously shown there, but whenever they ask this kind of question, you have to start with the question itself right away. Means they said, is there ever a time when v is equal to 0? So what will you do? You will all need to do is to put v0 in this equation first of all. Okay? So let me do this. V equal to minus 27 plus it is 3t squared. So since they are interested in time, well, there will be ever a time. So I need to determine what is the value of time. Add 27 to both sides, we will get 3t squared equal to 27. Because 27 will cancel out from this. Now divide both sides by 3. 3 cancels out, and 9 times 3 is 27, right? And then, since the t squared is equal to 9, you need to take the square root of both sides. Square root. The square root t is equal to given us plus minus 3. Well,
Sir,
can
we also say v equals 0 when the position is constant?
No. Yes, if the position is constant, if the position doesn't change with respect to time, then yes, it will be obviously 0. But that would mean that here you have this position and there will be no t, because now definitely the position depends on time. If so you want the position,
that can be an answer.
Yeah, no, that's not the answer, because the position here, when the way in which you are approaching to it, that you are saying the position is constant, while it is not. It is time dependent. The constant position should mean that it is only 4 or 10 or 20 or 100, something like that number, no variable. Okay.
Doctor,
okay. Yes.
How will be the time in negative?
Yeah, that's what I'm explaining. That's the point I'm explaining here. So here, when we got the time, we got the answer plus and minus 3. Okay, plus and minus 3 seconds. So normally, since our clock, we got used to it all the time, it goes running in the forward direction, and we say that there is no negative time. No, there is negative time. For example, I say that our class started at 12 p.m. But I can say that, where were you 30 minutes before my class? Okay, so when I say 30 minutes before my class, that will be negative 30. Where were you minus 30 minutes before my class? Okay, so if we like you spend 30 minutes in this class by now, then you can say I spent plus 30 minutes in this class. Did you understand this concept now? It is just the plus and minus, it tells you it is whether it is the time is before the experiment or after the experiment. Okay.
So we can say that there were 3 seconds before the speed up or something.
Yeah, so what we can say here, that when we started to observe, like let's say there is something oscillating, moving back and forth, the pendulum type thing, okay? We say that when we started to observe it, before that time, 3 seconds before that time, the object was at rest. And after, when I started my observation, after 3 seconds, the object is also at rest. Do you see?
Okay.
Yeah. Now, here I'm describe the motion of the particle for this situation. So here it is. The particle, it started when we put t equal to 0 in this equation. You see, t equal to 0. You see the second term and the third term will be 0. The x position when we get, it will be 4. So let's say it is in 4 meters, as they are saying it. So the position of the particle right there, it was 4 seconds at t equal to 0. Now, you started it and you put t equal to 1 in this. So you put 1 here and 1 here. So from this, when you solve it, it will be minus 27 and plus 5, which eventually it gives you minus 22. So minus 22 is your answer at t equal to 1 seconds. Okay? But you know that the answer, the displacement is negative because minus 22. You again put the t equal to 3, like which is here. 3, when you put 3 here and 3 here, the answer you get, it will be giving you x equal to 0. Okay? Not this way, not this way, no, sorry. When you put the 3 seconds here and here, what it gives you, that the velocity, it gives you 0, but the position of that is minus 50. And then after that, when you put like 4 seconds, then the particle is already coming forward because at 4 seconds, the positive value of this is more. So now the displacement will become positive after 3 seconds. Is there any confusion, guys, here? Anyone understand this step, or there is still something that I need to explain it?
Mr.
Can you explain it again?
Okay, all you need to do here is to take this, the equation of displacement, and this, you need to change the values of t. First, you need t equal to 0. Then you need to put t equal to 1. Then you need to put t equal to 2, 3, 4, and so on. Okay? And then every time when you put t equal to 0, let's say, you look at the value. T equal to 0, t equal to 0, it gives you 4. The 4 is positive. Okay? But let me explain the first one sentence. When you put t equal to 1, then here you will have 4 minus 27 plus 1. The answer of this is going to be minus 22. So minus 22 is definitely negative. So the displacement negative means that the object is now going in the negative x direction. Do you understand this step?
Yes.
Yes.
Okay.
Mr. I have a last question, please. For the first step, how did we get the 3 next to t square?
What is that?
How did we get 3 in the first step next to t square?
This one? You mean this one?
No, the A step.
A step, this one?
Yeah.
Minus 27 and plus 3 t squared, that's what you mean? This
yeah.
one?
How we did get the 3?
When you take the derivative of the 3 cube, what you get? Derivative of this t cube with respect to t.
Get 3.
Oh yeah, that's what we get.
Okay. Thank you.
Here is this checkpoint.
And a quiz tomorrow.
Yeah, quiz will be. I will be taking this quiz on the, not tomorrow, a day after. Okay.
Okay.
So tomorrow is Monday, and there will be Tuesday. So Tuesday in the class, the last 10 minutes, I will be taking a quiz, which will be a combined quiz for you all.
Okay.
What is the chapters do we have in the quiz? Chapter 1, 2, or just 1?
Guys, I need. Okay, I didn't finish really any of them. Okay. The time is. How much time do we have? Do you see it?
We have 1 minute left, sir.
Okay, let me introduce the constant acceleration a little bit. Okay.
And Mr. We didn't take the attendance yet.
Yes, I will give you this. So the constant acceleration here, when we are talking about I explained the instantaneous acceleration and the average acceleration. There is one thing, that's one thing which we know for sure. There is another thing, which is the constant acceleration. So sometimes when you are moving in a car, like in each interval of time, and that interval could be 1 minute, in each interval of time, your velocity can be more changed by more than one by some interval. Let's say from 20 to 100 you reached, but in the next interval you may not be able to reach from 100 to 180, right? So if that was the situation, then your acceleration is variable. But if you start your car, in the first minute you reach from 1 to 10, in the second minute you reach from 10 to 20, in the third minute you reach from 20 to 30. So in each passing interval of time, your speed increased by 10 kilometers per hour. In that situation, your acceleration is constant. Okay, so this is the main concept which we will be elaborating from here now. Okay, so tomorrow in the class, we will be doing problems, but afterward we will be covering some of the lectures next day. So let me give you the attendance. So on the derivative side, you guys need to pick up. Okay, this is something which we cannot spend too much time on it. Okay. Mahmoud, when you are putting this this WhatsApp group, it is a good thing for one reason and a bad thing for another reason. Usually this is leading up to bad behavior rather than positive behavior, right? Because oftentimes students are getting into the problems. Okay.
Oh, sir, I think the link doesn't work.
Okay, the link is a problem. Let me go to the link and activate it. Okay, this is one thing.
It just says it's closed. It's not.
Okay, so let's say it. Yeah, do that now. Is that working?
Yep.
Okay.
So are we done for today?
Yeah, we are done.
Okay, yes. Thank you.
Yeah, no problem.
Mr.
Yeah.
You told me that we must talk at the end of the lecture of today.
Yeah, so
I'm Ali Qahtani. I had a problem last week at Thursday.
Okay, what was the problem?
At the meeting, at the start of the meeting,